In, in this video, we are going to derive an integrated rate expression for first order reaction. So consider a reactant A Q's product. We have seen rate of the reaction in the last video. So how to write rate of the reaction for this? R is equal to minus dCA, means change in concentration or decrease in concentration of reactant with respect to time, or change in concentration of product with respect to change in time. Very small interval of time, here positive means increase in concentration. So rate law is KCA, the concentration of reactant. So we are dealing with the concentration, change in concentration of reactant. So minus dCA by dt can be written K is equal to CA. So rate comes here. Now, initially at time t, when the time is t, means the reaction could not occur, therefore the concentration of product will be C0. So at time t, the concentration is C0. This C0 is nothing but initial concentration. After certain time t is equal to t, your reactant A might have converted into the product. Therefore, there will be small amount of reactant is converted into product. So at that time, your concentration is C. We are taking concentration. So this is the concentration at particular time or after some time, once the reaction has started. So the rate dCA by dt minus dCA by dt is equal to KCA. So we are going to integrate this. So integrate minus dCA. To find the rate constant, we have to integrate. So integrated rate expression to find the rate constant of the reaction here for first order. So KCA, we are integrating in this here. So this minus sign you can take it out. So for integration, we have to implement this result. So at time t is equal to 0 to t, and concentration is 0 to C0 to Cc. So in the right hand side we have a concentration of reactant. So initially C0 and it is after some time C. So initially t is equal to 0 means or before that we can also we can here. So T0 or T0 you can indicate T. Now to simplify this integration, we have to separate the variables. So concentration bring it to this side, minus of T0 to T, or no, maybe after separable also you can apply the limit. That would be better understanding. Here just we will see the indicate. Here no need. First we will separate, then we will apply the limit. dCA divided by CA. We are bringing from here to here, left hand side to right hand side, and here integration of k dt we are taking this side. Now you can apply the limit. Initially it is C0 and now C. Initially it is T0 and T. So if we integrate dCA by CA, so minus I am keeping outside, it is ln CA. So we have limit C0 to C. If you apply the limit, upper limit minus lower limit, so ln C divided by, minus ln C naught. Similarly, this side, k you can take out, it is a constant. If you integrate dt, it is t. Applying limit is t0 to t. So since this is the first order reaction, the rate constant is k1. Here also you can change k1. So if you apply the limit right hand side, it is k into t minus t0. So at t0 it is 0. Therefore you can keep kt. If you apply the limit, this is 0. Right? So finally we have the equation. So here your bracket is there, ln C minus ln C naught equal to k into t. You can bring the sign in inside the bracket. So ln C naught minus ln C I can write is equal to kt. Ln C naught minus ln C, you can write it as ln C naught by C is equal to k into t. So this, if you bring this side, 1 by t ln C naught by C is equal to k. So this is the rate constant expression for the first order reaction. You can also find the concentration of C from this step. So I am continuing here. Take ln C naught minus ln C is equal to kt. You want to find the concentration of the reactant after time. So what you do? You make ln C naught by C is equal to k into t. So if you remove ln C naught by C, here it will come k into t. Now here we have made a little mistake. Here we can take directly from this. If you take, it is very easy. So minus ln C minus ln C naught equal to kt we have. So minus of in between ln C by C naught is equal to kt. So ln C by C naught, this negative sign you can bring it this side. So if you remove the ln, then it is C by C naught is equal to exponential of kt. So this C, if you keep here this side, C naught minus kt. So this is the concentration we can determine using this integrated reaction. So we have a rate constant expression, integrated rate expression, and also the concentration of first order reaction. So this C and C naught stands for the initial and concentration. So this I can also replace, like, again I am writing here, maybe new section I will go. So finally we have the equation, right? K is equal to 1 by T ln C naught by C, right? So we have A gives product. Initially the concentration, let us consider A, and here it will be 0 initially. After some time, what happens? Your X mole is formed. At that particular time, this concentration has becomes, concentration of reactant becomes A minus X. So this is C naught and this is C. So here time is equal to 0. After time, T is equal to T, right? So if you substitute this equation becomes